What is dark matter and dark energy? Dark matter, an undetected form of mass that emits little or no light, but whose existence we infer from its gravitational influence. Dark energy, an unknown form of energy that seems to be the source of a repulsive force causing the expansion of the universe to accelerate. In the last 2 decades, we have come to realize that the dominant source of gravity in the universe is dark form of matter that differs fundamentally from the atoms that make people, stars, and galaxies. In addition, there appears to be dark form of energy throughout the universe that counteracts gravity and is the driving force of the expansion of the universe. When it comes to the recipe of our universe, more is unknown than known. We know how much dark energy there is because we know how it affects the universe's expansion. Other than that, it is a complete mystery. But it is an important mystery. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up about 27%. The rest, everything on Earth. Everything ever observed with all of our instruments, all our normal matter, adds up to less than 5% of the universe. Come to think of it, maybe it shouldn't be called normal matter at all, since it's such a small fraction of the universe. Hubble's Law. The American astronomer Edwin Hubble made the observation in 1925 and was the first to prove that the universe is expanding. He proved that there is a direct relationship between the speeds and distance of galaxies and their distance from Earth. This is known as Hubble's Law. In 1998, the Hubble Space Telescope was able to discover, through observing supernova, that the universe is expanding faster today than it has in our universe's history. The yet-to-be-discovered solution was termed by the astronomer as dark energy.
The rotation curve of galaxies are flat. This in turn points towards that most of their matter lies outside their visible regions. This is different than astronomers expected to find. What we expected was more like a merry-go-round. As further you get from the center, the orbital velocity rises. For stars in orbit around the central mass of the galaxy, we expect the rotation curve to decline, but the rotation curve of the Milky Way galaxy stays flat as distance increases. From this, we can conclude that mass is spread out throughout the solar system. Mass in the Milky Way is spread out over a larger region than the stars, and it does not glow like stars and nebulae. Because the rotation of large bodies in the universe does not change when moving closer and further from other bodies, we conclude that a mass has to be acting around each body to stabilize it. This outside mass is dark matter surrounding the body. Dark matter, even though unseen, is present in great quantities, essentially providing the foundation and keeping galaxy clusters intact and in rotation. Furthermore, there is more evidence within large galactic clusters that have giant pools of hot gas that account for some of the mass in the clusters. Scientists used the Chandra X-ray Observatory to see if these gases were making up all of the undetected mass that was within these large galactic clusters. Instead, the scientists discovered that there is not enough mass in the stars and hot gases to make up the gravity that was measured. There is up to 5 times more mass than the stars and gases make up. Gravitational lensing is the bending of light rays by galaxies. Dark matter will then expose itself by bending light that passes through it. So gravitational lensing essentially is a virtual spotlight that uncovers any visible materials within the universe. We see deflected light rays by tracing battered light paths to detect dark matter concentrated in the halo of galaxies. Gravitational lensing reveals much more mass than we can see in starlight from these galaxies, which is more evidence for truly dark matter. All three methods of measuring cluster mass indicate similar amounts of dark matter as well.
4 dark matter candidates are machos, WIMPs, neutrinos, and axions. Machos are massive compact halo objects. They're basically small dark stars that don't give off a whole lot of light. They're high in mass and present throughout the entire universe. There's not enough of those to account for the dark matter needed, though, so scientists have concluded that dark matter is not made of machos. Another idea is WIMPs. WIMPs are not any form of ordinary matter, but weakly interactive massive particles that could be leftover matter from the Big Bang. WIMPs do the best job at explaining how galaxy formation works because these particles do not feel electromagnetic or strong nuclear force. They feel gravity and weak forces only. WIMPs cannot collapse either, since they can't radiate energy. If WIMPs are the correct solution, theory says that they were created during the Big Bang, but as temperatures dropped, they lost their density, but continued to still annihilate each other while not reproducing at all. At some point, the temperature dropped low enough that density loss was halted and annihilation became infrequent enough for them to sustain existence. Neutrinos and axions are not as strong of candidates as WIMPs. The idea that dark matter consists highly of frozen neutrinos, though, has been proposed by some astronomers. Conventional neutrinos move too fast to be the dense dark matter that we detect today. There is a significant link between the two as they have a similar mass when considering a frozen neutrino. In this theory, dark energy is the result of neutrinos when paired with accelerons being pulled apart. This causes the universe around the interaction to expand. This is a difficult idea to prove since neutrinos come in different flavors. Another idea is axions. Axions are small hypothetical particles that, if exist, solve the small CP problem in quantum chromodynamics. If these particles do exist, they are a good candidate for dark matter at certain mass levels. The axion is a neutral particle that is extraordinarily weak interacting and could be produced in the right amount to constitute dark matter. Little progress has been made to prove existence of axions so far. As we noted earlier, dark energy is causing the expansion of our universe. Dark energy is built up momentum left over from the Big Bang. Dark energy accelerates the expansion process quicker over time. We see the effects of dark energy in the brightness of distant white dwarf supernovae that tell how much the universe has expanded since they exploded. Dark energy has been said to be like a coiled up spring releasing energy. Currently, there are three main ideas or theories as to how the universe will come to its end due to dark energy. One scenario for the end of the universe is called the Big Freeze. In this theory, the universe keeps expanding and slowly runs down to a state of no thermodynamic energy enough to where it is unable to sustain motion or life. Eventually, all the universe would be is burnt out stars, dead planets, and black holes. The second is the Big Crunch, which is essentially the opposite of a Big Bang. Dark energy means the universe would expand forever, but if the universe were to lack the repulsive effect of dark energy, then gravity will eventually halt universe expansion. The universe will contract until all of the matter in the universe collapses back into the opposite of the Big Bang. The third is the Big Rip. In this scenario, all of gravity's work is undone. Clusters of galaxies will separate due to expansion, and eventually galaxies themselves will be torn apart. The solar system, stars, planets, and even molecules could be shredded.